Hey guys, let me just put up a warm up here. So let's see, how about this? So suppose f and g are integrable. Oh, rather continuous. Let's see. The integral from a to b of f is the integral from a to b of g. All right. Yeah. Let's resume at like 5 5:13 or something. All right, hey guys. Let's go over the warm up here. So, what is the main theorem that we want to use in the solution?
Intermediate value theorem for integrals.
Yeah, exactly. But we can't just directly apply it to f and g, right? How do we have to do this?
We'd have to move one on the other side and define h as f minus g.
Yeah, exactly. So, yeah, let's say h is f minus g, right? Then by the linearity of integrals, the integral from a to b of h is the integral from a to b of f minus the integral from a to b of g, which is 0, right? So by the intermediate value theorem for integrals, there exists an x in AB such that h of x is 1 over b minus a times the integral from a to b of h, which is 0, right? So f of x equals g of x for this x, right? What's the actual problem, right? What would be the problem if we applied the intermediate value theorem for integrals to each of the two functions separately?
You wouldn't know if it's the same x.
Yeah, exactly. Yeah. We might get like different values of x. Like we would get one value of x where f of x is the average value of f, because they do have the same average value, right? But we would get one value of x where f is the average value and one value of x where g is the average value, but they might be different. So yeah, that's why this trick is sort of necessary here. Any questions about that? Or general questions? Okay, then I figured what we could do that I think is a pretty good exercise, and it's also actually like pretty useful just in general, is yeah, these exercises that basically show that if f and g are integrable, then f times g is also integrable. So there's like two exercises at the end of this that like combined, they go through this proof basically. So let's do that. I think that would be good. So let f be a bounded function on AB, say so first part here is show that the upper sum of f squared on some partition minus the lower sum is less than or equal to 2b times the upper sum of f minus the lower sum of f. Use this to show if f is integrable on AB, then f squared is also integrable on AB. And then lastly, I'm kind of like mashing the problems together here. Show that if f and g are two integrable functions, on AB, then fg is also integrable. And they give a hint, which is this. Oops. For fg is squared minus f minus g squared. All right. Yeah, so let me make some rooms. Yeah, I'll just make one for the 5 of you. So yeah, let's say this is a little bit more substantial of a problem. So let's say we'll reconvene at like 5:33, 5:35. I don't know. Yeah, let's say like 5:35. Oops.
What does it mean two integral, like twice integrable functions, or they're two
No,
different
they're just two
integral?
different functions
Okay,
that are
cool.
both integrable. Yeah, both. All right. So, yeah, I think it's probably part A is like a little bit difficult, maybe. At least I don't know. Yeah. Well. So let's look at part A. So, right. We have that. So U F squared P minus L F squared P. That's going to be the sum of k equals 1 to n of like the like capital M of f squared tk minus 1 tk minus the little m f squared tk minus 1 tk all times tk minus 1 tk what minus tk minus tk minus 1. Yeah. So that's this. So it's all about like dealing with this. Like we want to show this is less than or equal to like 2b times capital M f tk minus 1 tk minus little m f tk minus 1 tk. Right. As long as we can do that, like that suffices to prove the whole thing. So let's just like focus on this, right? So I don't know. Were you guys able to like to show this? Does anyone have any suggestions for how we might proceed?
Well, idea. I know like if absolute value of x is less than b, then absolute value of x squared would be less than b squared,
Mm-hmm.
right?
Yeah, that's true.
So can we use that here somehow, like for f of x?
The problem is like, okay, if you go that way, you're gonna like somehow lose this part of what we're trying to show. So like it's hard to explain like the intuition behind this, but you can't just directly you can't directly bound f squared above or below by like a constant, because then you're just going to end up with like a constant here. So you'll end up with like a constant multiple. You'll basically end up with a constant for this entire expression if you use too many constant upper bounds. And the problem is like we want to like preserve this like feature of it, so that way we can end up with the thing proportional to like this, right, in the end. Because the thing is, we have the power to make this small, right? And so if we just end up with a constant instead, we won't be able to like force that to be small, basically. So it requires a little bit more delicacy. So here's what I would say. It's a little bit weird, but so I think you can just say like, okay, mf squared this is like, oh wait, it goes, oh yeah, this equals the supremum of like f squared x, or let's say f of x squared minus f of y squared.
Oh,
For like x and y So you can do like this two-dimensional. You can kind of have this like two-dimensional, like a set that's parameterized by like two variables basically, and then so this is like supremum of, and this just factors as a difference of squares. And then I think you can just say, so this transition is like, arguably that requires a little bit of justification. It's not hard, but you know, we can get into that in a sec. But if you just believe this for now, then I think then this I think is like less than or equal to. So then I think you can like factorize it. And this also might require some justification. So we would have like f of x plus f of y. Actually, hmm. Yeah, there's like a little bit, there's a little bit of like delicacy because actually, okay. I'll get into this in a second. Okay. So there's some, so this is actually like not totally valid, I think, without more justification. And then like x and y. And then this one, so then, whoops. Well, yeah, I'm kind of running out of room. So this supremum should be, well, this one is just like, this is less than or equal to 2b, right? And then this one is actually less than or equal to big M of f minus little m of f. So this is directly like less than or equal to 2b, big M minus little m. I'm not going to write all this stuff, but yeah.
That not totally valid inequality thing, but that does make sense because it's bounded, right? That you can split it up, or no?
Yeah, it's not, it's okay. It is valid. It's just like the justification is not immediate, basically, because basically like there are some pairs x and y where this may be negative. So you have to, basically there's like a symmetry principle here where it's like for every pair x and y where this is negative, by flipping the pair x and y, you can turn this into a positive. So this whole set, the set of values here, the set of like all of these values is symmetric. It's symmetric about zero, basically. So it's really that fact. Like you have to actually like use that fact to justify why this is valid, because it could be possible that like in theory, it could be possible that there are values of x and y where and like also both of these two sets individually are symmetric about zero, so that's like also important. But like in theory you could, oh wait, no, this one is not symmetric about zero. Wait, let me think for a second. Oh, okay. You know what? This is actually wrong. Sorry. This is just like not. Yeah, actually what it should be is like I think just like absolute value. Yeah, if you put absolute values, then it should be fine. Yeah. Yeah. In fact, what you can do is I think this supremum should equal the supremum where you have like absolute values here. And then, yeah. Yeah, I think you can put absolute values around everything. Well, either way, you can, yeah. I think you don't have to do that. But as long as you put absolute values here, then that actually, otherwise it's actually like not even true, because it's possible that if f is just like a negative function like everywhere, right, then it's possible that this is a totally like positive number up here, but this supremum down here might actually be negative, and then this one will still be positive. So you'll end up with a negative number over here, and that you don't want that. So that, yeah, without the absolute values, it's just not right. But with the absolute values, this works. And if you want, you can go through carefully, like you can do kind of the, or you can go like element wise. You can say like, okay, any element of this set, like any number of this form is less than or equal to like this, basically, right? So like it's like what you can do is like say x and y. Oops. Also, this should not be, sorry, these should not be r. It should be like a tk minus, yeah. All of these should be like tk minus 1, tk. Sorry.
Wait, question. Do we need the absolute value on f of x minus f of y?
No. Because like I said, so what I was saying is that like it doesn't matter whether you put the absolute value there. You can put it there or not, right? But the thing is that like no matter what, like the supremum, oops.
Oh yeah, okay.
The supremum of the set can't be negative. Yeah, exactly. Yeah. And like for whatever, any negative values that might be in this set, they're the negative of that, like the positive versions of those values are also in the set. So yeah, that's what I mean when I say it's like symmetric about 0. That's what I'm talking about. So yeah, yeah, good, but good question. Yeah. So right, so you could say like, right, and we want to show like f of x squared minus f of y squared is less than or equal to like this. Right. So this equals f of x plus f of y times f of x minus f of y. Yeah, I mean, I guess it's just obvious. Like this is directly less than or equal to this, right? Because it's less than or equal to the absolute value of itself. And that's less than or equal to this. And then this is just directly less than or equal to that. Yeah, I guess it's okay. I guess it's just like kind of trivial, actually. This part is kind of trivial, I guess. And then this one, yeah. I mean, this one takes a little bit more work, maybe, but yeah. The way I think about it is like this. So like, sorry, squared. This is like, okay, so on one hand we have this like supremum of right? And then we have this minus little m of whatever. So what you can do is if you just think about this as like a constant, you can like move this inside. So this is like the supremum of like f of x squared minus little m of f squared tk plus 1 tk, right? And for x in right. And then you can say like this is like so this is f of x squared minus the infimum, but that's the same thing as like the supremum of f of x squared minus f of y squared for y in t k minus 1 tk. So you kind of get these like nested suprema. So overall, like capital M of f squared, whatever, minus little m of f squared, whatever, is like the supremum of f of x squared minus f of y squared, where you're quantifying over y in here. And then you're quantifying over x out here. But then almost by definition, actually, this is like just, well, not really by definition, but it's sort of trivial that this is like, that you can just like collapse the quantification. Because the supremum of all these suprema is just going to be the supremum of this overall thing, basically. Okay. So yeah, you can just get this like sort of doubly indexed supremum like this. Oh, I guess yeah, and then do this. Yeah. Yep. I think that does it for the first part, at least. Any questions about that? I know this is kind of like a technique that like maybe didn't occur to you because we haven't really done stuff quite like this before, I guess. But like it should be, I don't know, maybe it'll help if I kind of talk about like the intuition that I had in my head when I was thinking about this, because basically the idea is that here it's like the biggest value, like, well, okay, ultimately it's like we would like to get to this expression somehow, because that's where we can actually use the like difference of squares factorization to our advantage, right? So the whole point is that this is like the biggest value of f squared on, you know, tk minus 1 tk, sort of, quote unquote, and this is like the smallest value, right? And so it's like, it's not equal to the supremum of f of x. Well, yeah. I mean, so basically it's like, you know, if you imagine like sort of finding the biggest value somewhere in the interval tk minus 1 tk, like if you kind of pretend that f was continuous, for example, if you pretend that f is continuous, then like this is actually the maximum value, right? And it occurs at some like x value in this interval, tk minus 1 tk. And then this is the minimum value, and that actually occurs somewhere in the interval tk minus 1 tk. And they might occur at different places, but if you found the maximum value and the minimum value, and then you're subtracting them, that's going to be like basically bigger than any other like difference that you could possibly get. Because if you take if you take like two other x values and try to subtract f squared, the values of f squared of those, right? The one that you're like, the first one, right, is going to be smaller than this maximum, and the second one is going to be bigger than the minimum. So the difference is going to be like smaller, right? So I don't know. That's just kind of how like that image just automatically suggests this idea, at least to me. I don't know. Yeah, and then it's like once you have this difference of squares, you can actually like use it and do stuff like this. Okay, so And it's weird, you know, I don't know. I don't actually, I'm kind of curious. Oh, this is odd numbered. I think that means that the book itself, actually, one sec. Let me look at what the book says. I think they have solutions for the odd numbered ones. Okay, they just like don't even they just, they just say like, yeah, for any s and x not y not in s, we have f of x squared minus f of y not squared. Oh yeah, they do use the absolute values actually. Okay. And then they just say it follows that capital M of f squared minus little m of f squared is less than or equal to this thing. Yeah, all right, whatever. I mean, it's basically the same as what I said, just a little bit cleaner notationally and with a little bit less explanation. When they say it follows, it's like they definitely could explain that a little bit more. But I think they're intentionally kind of cryptic with these because they don't want to like give, like, they don't want to just like lay out the entire solution, I guess. All right, anyway, whatever. Let's finish off this. So the second two parts, given the first part, are like not that bad, right? Because basically for the second part, right? So for B, so if we like let epsilon be greater than 0, then pick P such that like U of FP minus L FP is less than epsilon over 2B, then by A, right? U F squared P minus L of F squared P is less than or equal to 2B U F P minus L F P, which is less than 2B, right? So F squared is integrable by whatever that theorem was, 32.5 or something. Yeah. Right. And then, all right, I did all this stuff. And then for C, oh yeah, it's showing that FG is integrable. Well, so this is just a long chain of like, okay, if F and G are individually integrable, right? Then F plus G and F minus G are integrable. That's from the theorem with linearity. And then, so F plus G squared and F minus G squared are integrable. That's from part B. And then, so you can add them together or subtract them, I guess. That's linearity again. And then you can divide by 4. That's again by linearity. Right. And this is just FG. So yeah, there you go. Any questions? Yeah, okie dokie. Yeah, then that'll do it for today. So yeah, we have one more discussion tomorrow, which will be focusing on like the section 34 stuff. And then and then there will be a review on Wednesday. That'll be like 2 hours. And I'll have office hours as usual on Wednesday morning. Obviously, I'm not going to have office hours on Thursday because that's the final. But yeah, other than that, yeah, that's all. So see you guys.
Thank you.
Yep.
Thank you.